Download this code from codegive.com, link in the description below. Understanding dangling pointers, a comprehensive guide. Dangling pointers are a common source of bugs in C and C++ programs. They arise when a pointer holds the address of memory that has been deallocated, or the object it pointed to has gone out of scope. Dereferencing a dangling pointer can lead to unpredictable program behavior, including crashes, data corruption, and security vulnerabilities. This tutorial will provide a detailed understanding of dangling pointers, explore their causes, and illustrate how to avoid them with code examples. 1. What is a dangling pointer? A dangling pointer is a pointer that stores the address of a memory location that has been freed. The memory was previously allocated, example using malloc in C or new in C++, but has since been released back to the system using free in C, or delete in C++. Is no longer valid. The object it pointed to has gone out of scope, meaning its memory is no longer guaranteed to hold its original value. This often happens with local variables within functions. Think of it like this: imagine you have a piece of paper, memory location, with a phone number, data, written on it. You give that paper to someone, a pointer. Now, you erase the phone number from your paper or throw the paper away, free the memory. The person still has the paper, the pointer, but the information on it is now either incorrect or non-existent. Trying to use that phone number now could lead to calling the wrong person or even a disconnected line. 2. Causes of dangling pointers. Let's examine the common scenarios that lead to dangling pointers. A. Explicit deallocation, dynamic memory. This is the most direct and frequent cause. When memory is dynamically allocated using malloc, in C, or new, in C++, it's the programmer's responsibility to free or delete that memory when it's no longer needed. If you delete the memory but don't nullify the pointer, you have a dangling pointer. See example asterisk. C++ example asterisk. Explanation asterisk. Asterisk in both examples, memory is dynamically allocated using malloc, C, or new, C++. Asterisk the allocated memory is then explicitly freed using free, C, or delete, C++. Asterisk after freeing the memory, PTR still holds the, now invalid, address, making it a dangling pointer. Asterisk attempting to dereference PTR after freeing, the commented outlines, leads to undefined behavior. This means the compiler is allowed to do anything, including crashing the program, corrupting data, or appearing to work correctly, which is the most dangerous because it hides the bug. Asterisk the solution is to set the pointer to null, C, or null pr, C++, after freeing/deleting the memory. This makes it easy to check if the pointer is still valid before dereferencing it. B. Returning a pointer to a local variable asterisk. When a function returns a pointer to a local variable, the pointer becomes dangling as soon as the function returns. This is because local variables are stored on the stack, and the stack frame is deallocated when the function returns, making the memory pointed to by the returned pointer invalid. Explanation asterisk. Asterisk create_number declares a local variable number. Asterisk it returns a pointer to number. Asterisk after create_number returns, the memory allocated for number is no longer valid. The stack frame associated with create_number is removed. Asterisk PTR in main now holds the address of this invalid memory, making it a dangling pointer. Asterisk attempting to dereference PTR results in undefined behavior. The value it points to is likely garbage, or the memory might be used for something else by the time main tries to access it. How to fix this asterisk? 1. Allocate the memory dynamically *use malloc, in C, or new, in C++, to allocate memory on the heap. The heap memory persists until it is explicitly freed/deleted. This means the calling function is now responsible for managing the memory. To return a copy of the value *, return the value directly instead of a pointer. This avoids the problem of dangling pointers altogether. 3. Pass a pointer as an argument, output parameter. Modify a variable passed by reference, in C++, or through a pointer, in C, in the calling function. This avoids the need to return a pointer to a local variable. C. Deleting an object used by multiple pointers, shared ownership. If you have multiple pointers pointing to the same object and you delete the object using one of the pointers, the other pointers become dangling. This situation arises when objects are shared between different parts of a program. Explanation ****. PTR1 and PTR2 both point to the same dynamically allocated memory. **delete PTR1 frees the memory. **PTR2 is now a dangling pointer because it still holds the address of the freed memory. Dereferencing PTR2 after the delete PTR1 statement leads to undefined behavior. Setting PTR1 equals null prevents accidental use of PTR1. However, PTR2 remains a dangling pointer, and dereferencing it will still be problematic. How to avoid this asterisk? 1. Ownership semantics clearly define which part of the code owns the object. The owner is responsible for deleting the object. Other parts of the code that use the object should only hold raw pointers to it temporarily and never delete it. This approach requires careful coordination and documentation. 2. Smart pointers. C++ use smart pointers like std unique _ptr and std shared _ptr in C++. These provide automatic memory management and help prevent dangling pointers. *std unique _ptr enforces exclusive ownership. Only one unique _ptr can point to a given object. When the unique _ptr goes out of scope, the object is automatically deleted. This prevents accidental double deletion and helps avoid dangling pointers. *std shared _ptr allows multiple pointers to share ownership of an object. A reference count is maintained. When the last shared _ptr pointing to the object goes out of scope, the object is automatically deleted. This helps manage shared resources safely and prevents dangling pointers. 3. Techniques for avoiding dangling pointers. Here's a summary of practical techniques to prevent dangling pointers. 1. Initialize pointers * always initialize pointers when you declare them. If you don't have a valid address to assign, initialize them to null, C, or null pr, C++. This helps to avoid accidental dereferencing of uninitialized memory. 2. Nullify pointers after freeing/deleting * immediately after freeing memory using free, C, or delete, C++, set the pointer to null, C, or null pr, C++. This explicitly indicates that the pointer is no longer valid. 3. Check for null/null pr before dereferencing * before dereferencing any pointer, always check if it is null, C, or null pr, C++. This prevents crashes due to dereferencing invalid memory. 4. Avoid returning pointers to local variables * as discussed earlier, avoid returning pointers to local variables from functions. Instead, return copies of values, dynamically allocate memory, or pass variables by reference/pointer. 5. Use smart pointers. C++ employ std unique _ptr and std shared _ptr to automate memory management and prevent dangling pointers in C++. 6. Defensive programming *. Write your code defensively. Consider the possibility that a pointer might be invalid before using it, and add checks accordingly. 7. Code reviews *. Conduct thorough code reviews to catch potential dangling pointer issues. 8. Debugging tools *. Utilize debugging tools like memory leak detectors, example Valgrind, and debuggers, example GDB, to identify and diagnose memory-related problems. These tools can often detect invalid memory accesses, including those caused by dangling pointers. Address Sanitizer is a tool often used for finding these type of errors. 4. Consequences of dangling pointers. Undefined behavior *. The behavior of a program that dereferences a dangling pointer is undefined. This means anything can happen. The program might crash immediately, corrupt data silently, or appear to work correctly for a while and then fail later on. Security vulnerabilities *. Dangling pointers can be exploited by attackers. If an attacker can control the contents of the freed memory, they might be able to inject malicious code and gain control of the program. Difficult to debug *. Dangling pointer errors can be notoriously difficult to debug because the symptoms might not appear until much later in the program's execution, and the root cause might be in a completely different part of the code. In summary, understanding dangling pointers is crucial for writing robust and secure C and C++ programs. By carefully managing memory, initializing and nullifying pointers, using smart pointers, in C++, and employing defensive programming techniques, you can significantly reduce the risk of dangling pointer errors. Always remember to check for null/nullpr before dereferencing and use debugging tools to help identify memory-related problems early on. By mastering these concepts, you'll be well on your way to writing safer and more reliable code.